So in this video, we will learn about series and parallel circuits. So which of the two circuits is series or parallel? So I have here a circuit on the left and a circuit on the right. So which of these two circuits are parallel? So in this case, series circuits is on the left. So the reason behind this is that there is only one path for the current to flow. So the current can flow from here. Whereas in parallel circuits, there are one or more than path for the current to flow. Current can flow here and also can flow here. So in series circuits, so by the way, you can view resistors as light bulb. So in series circuits, as you add more light bulb in series, the light will be more dimmer. It's because there is a less current flow through the light bulbs. So as you increase the number of resistors, there is a less current flow in series circuits. Okay, lesser current in series circuit. However, in parallel circuits, it doesn't matter how many light bulbs you will connect because there is an enough current that will flow in parallel circuits as long as you have a strong battery that can provide um, current or there is enough current drawn from the battery. So in parallel circuits, as you increase um, oh no, but rather in parallel circuits, as you increase the light bulb, the resistance decreases while the current increases. So there is enough current that will flow in your circuit and still the light bulb will light. Okay, so let us solve for a series circuits. Okay, so let's keep this in the side and we'll solve for series circuit. So our first step in solving the series circuit is first we will determine the total resistance. Now, you can determine the total resistance using this equation. So total resistance RT is equal to R1 plus R2 plus R3. Or if there are more resistance connected in series, you can use this formula to Rn. So in this case, since we have two resistors connected in series, so we can compute R total is equivalent to R1 plus R2. So in this case, in our series circuits, let's say we have an applied voltage of 10 volts and our R1 and R2 is equal to 3 ohms and 2 ohms respectively. So we can now therefore find the total resistance. So total resistance is equivalent to 3 ohms plus 2 ohms. So we have total of 5 ohms total resistance. Okay, so our next step is to solve for the total current that is flowing in the circuit. So by the way, here in the circuit, in the conventional current flow, so current flow from positive to negative. So this is because it follows the flow of positive charges. However, electrons flow from positive to from negative to positive. Okay, so here we'll just use the conventional current flow. Okay, so our next step is to solve for the total current flowing in the circuit. So we can actually we can use the Ohm's law. So using the formula V is equal to IR. So since we have now our total voltage, which is 10 volts, I times our total resistance 5 ohms. So we now have current as 10 volts all over 5 ohms. So we have 2 ampere that is flowing in our circuit. So this is now our total current. So total current 2 ampere. Now after this, we can now solve for the voltage drop across its resistors. So to find for the voltage drop, we can still use the formula V is equal to IR. Since we already know the current, so in series circuits, the total current flowing in the circuit is equal to the current across its resistors. So it illustrates this equation, IT is equal to IR1, or current across R1 is equal to IR2, or dot 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 equal to IRN in series circuit. So here we have VR1, voltage across, or the voltage drop across resistor 1 is equal to the 2 ampere multiplied by the resistance, which is 3 ohms. So VR1 is equivalent to 6 volts. So here, this is now the 6 volts. So we have now 6 volts. And for VR2, we have 2 ampere multiplied by the 2 ohms resistance. So we can have our VR2, which is equivalent to 4 volts. So we have now 6 volts and we have now 4 volts. Notice that the two voltage drop will add up to our applied voltage, which is 10 volts. So this 6 will add up to 10 volts. Actually, it satisfies the Kirchhoff voltage law. So actually, Kirchhoff voltage law states that, or KVL states that for any closed loop in a circuit, the sum of the potential difference across all components is 0. So as you can see, so we as you can see, we have 6 volts voltage drop across R1 and also 4 volts across R2. So the positive terminal of the battery has greater potential difference than the negative terminal. So we have this point. So this is 0 volts and this is 10 volts. So in this point, this is 4 volts. Now, from the negative, or from 0 volts, or from the negative terminal to the positive terminal. So since it is, let's go clockwise. So we have positive 10 volts. And from 10 volts to 4 volts, we have a voltage drop, which is 6 volts. So minus 6 volts. And from the full volts, we have again a voltage drop 4 volts. So minus 4 volts. So 10 volts minus 6 volts minus 4 volts then is equivalent to 0 volts. So therefore, it satisfies the condition that KVL uh, states that for any closed loop in a circuit, the sum of the potential difference across all components is 0. So actually, it satisfies the KVL. As you will observe, that the summation of all voltage across the circuits is equivalent to 0. Okay. Now, our next step is to solve for the power. So, let us resize this one so that we can have more spaces. Let's just delete this one. Okay, so our next step is to solve for the power. So we will solve for the power delivered by the battery, and also the power that is consumed or that is absorbed in its resistors. So here we can use the formula for power is equal to P is equal to IV. So power is equal to the current times the voltage. So we will solve for the power delivered by the battery and the power absorbed by its resistors in the circuit. So resistor are 3 ohms and also 2 ohms. So since we have now the total voltage, okay, by the way, we can also derive other formula from of power. So if we will consider, since P is equal to IV and also V is equal to IR, so if we will substitute V in the power formula, so we can have IR times, oh yes, we can have IR times I times IR. So we have power is equal to I squared over I squared R. So this is now our first formula. This is our second formula. Also, from V is equal to IR, we can have I is equal to V over R. If we will substitute I in the first equation, so we can have power is equal to um, V over R multiplied by V. So we can have our third equation, which is V squared over R. So we can use these three formulas in computing the power absorbed, the power delivered by the battery in our circuit. So here we can compute now the total power of the circuit. So P is equal to the total current 2 ampere that is flowing in our circuit times the voltage, which is 10 volts. So we can now compute the total power, which is equivalent to 2 watts. So this circuit or the 10 volts battery delivered 20 watts power for these circuits. So we have 20 watts. Now we can solve for the power across each resistors. So the power across resistors. So shall we let's say we will use this formula. So P is equal to I squared R. So P, the total current is 2 ampere squared multiplied by the resistance across R1, which is 3 ohms. So the power is equivalent to 12 watts. So we have 12 watts absorbed by resistor 1. And for resistor 2, so let's have more spaces here. Let's make more spaces. So for R2, we have P, shall we say we will use the third equation, V squared over R. So power is equivalent to the voltage drop across R2, which is 4 volts. So 4 volts squared over the resistance across on R2, which is 2 ohms. So we have 16 divided by now 2 ohms. So we have 8 watts. So we have 8 watts across R2. So notice that the two power absorbed by resistor R1 and R2 will add up to our total power delivered by the battery for the circuits, which is 20 watts. Now, what is really meant by power? What is exactly power? So let's say we have power can be described as work over time. So power is equivalent to work over time. So this is 1 watt is equivalent to 1 joule. So 1 joule over 1 second. So there is a 1 watt power delivered which is from 1 joule per unit of time. So we have 1 watt. So example, we have 100 joule. Let's say for example, we have two systems that will deliver work 100 joule. So the first system deliver 100 joule over or per second, and the other system um, perform work over 10 seconds. So which of the system um, will perform faster? So in this case, the first system perform faster than the other one, since um, it it delivers or it performs work in 1 second. So it has a faster rate than the other one, since um, the other system also deliver the same or perform the same work, however on a slower time, so which is 10 seconds. So since this is a slower time, the second system performs slower time or slower rate, so we have 10 watts. So this is 10 watts. So it will deliver power 10 watts in 10 seconds. And while the other one, it will deliver power 100 watts in a second. So the first system is much faster than the other system. So power, therefore, is a rate. Power, therefore, is a rate of change of energy per unit time, per unit of time. Okay? So that is power. So let's say we have, let's go back to our previous example. our circuit, the battery of the circuit delivers 20 watts power. So, so we have 20 watts power. So 20 watts power. Let's say, for example, we will try to run the circuit. We will allow to run the circuit for a certain time, and the time is equivalent to 10 minutes. So work is equivalent to P times time. From the formula, power is equivalent to work over time. Now, since this is a power, we are talking about um, we are talking about running the system in 10 minutes. So we can now first convert the time into second and multiply it with how much power that is delivered by the circuit or the battery, drawn from the battery. So we will convert 10 minutes. Oh yes, so 10 minutes, we have 1 second. 60 second is equivalent to 1 minute. And let's say, for example, since the battery drawn from the circuit is 20 watts per second, so we can now cancel this one, also this one. So we can have 12,000 watts or 12,000. Pardon. This is joule. So it delivers, since 20 watts, so this is a joule. So we have now 12,000 joule or 12,000 kilojoule. Okay, so that's it. So our circuit performs 12,000 kilojoule. So as equivalent to the power that is 20 watts. So this is for series circuits. So let us have more example for series circuits. So let us have another problem. So let's say, for example, we have the circuit. So R1, R2, and R3. So we have R1, R2, R3. So this is equivalent to 1.8 kilo ohms. This is equivalent to 1.2 kilo ohms. And we have 1 kilo ohms. So our circuit is supplied by a battery which is equivalent to 24 volts supply. Okay, so our first step is to find for the total resistance. Total resistance can be computed by this formula. So R1 plus R2 plus R3. So our total is equivalent to 1 kilo ohms plus 1.2 kilo ohms and 1.8 kilo ohms. So our total resistance is equivalent to 4 kilo ohms. So by this, since we have now our total resistance, we can now therefore find the total current that is flowing in the circuit. So using this formula, V is equal to IR. So we know already that the voltage is 24 volts and our total resistance is 4 kilo ohms. So we have now the current, which is equivalent to 24 volts all over 4 kilo ohms, and the total current that is flowing in our circuit is equivalent to 6 milliampere. So since this is series circuit, the total current that is flowing in our circuit is also equal to the current that is flowing in its resistors. So IT is equivalent to the current across R1, current across R2, and current across R3. So by this, we can now compute the voltage drop across each resistors in series. Okay, so we have now VR1, which is equivalent to 6 milliampere multiplied by the resistance R1, which is 1 k ohms. So VR1 therefore is equivalent to 6 volts. For VR2, we have 6 milliampere multiplied by 1.2 k ohms. VR2 is equivalent to 7.2 volts. For VR3, so we have 6 milliampere multiplied by 1.8 k ohms. VR3 is equivalent to 10.8 volts. So we have this one, and this one. So as you notice, we have, if you sum up all the voltage drop across each resistors, it will add up to our applied voltage, which is equivalent to 24 volts. So we have current that is flowing in the circuits, which is 6 milliampere, and our total resistance, which is 4 k ohms. Now, so we have 6 volts here, we have 7.2 volts here, and we have 10.8 voltage drop across R3. So still, this is the same with the previous circuit that we solved earlier. However, there is one more resistor that is added in the circuit. So here we have 18, since we have 24 volts here, and we have 0 volts at the lower potential difference. So we have 18 here, and we have 10.8 here. So this is 18 volts. Now, the circuit or the voltage flow here, so from negative, so from 0 potential difference to positive to the 24 potential difference, so that is equivalent to positive 24 volts. So from 24 volts to 18, we have a voltage drop of 6 volts, so minus 6 volts. And from 18 to 10.8, we have a voltage drop of 7.2 volts. And the last one, we have 10.8 voltage drop across resistor 3. And it will sum up to 0 volts. So still, it satisfies the condition or the law of Kirchhoff voltage law, which states that for any closed loop in a circuit, the sum of the potential difference is always, of all components, is always 0. Okay, so that's it. So we can now compute also for the power. So here, So we can have PIV. Power is equivalent to, since we have now our total current, which is 6 milliampere. So we can now therefore compute for the total current delivered by the 24 volts battery in the circuit. So we have 6 milliampere multiplied by the total voltage, which is 24 volts. So that is equivalent to 144 milliwatts. So let's try to compute this in calculator. 6 milliampere times 24. Yes, it is equivalent to 144 millivolts. Now let us compute for the power absorbed for resistor 1, PR1. So we have 6 milliampere. Let's say we will use, yes, we will still use this equation. PR1 times the voltage drop across resistor 1. So the voltage drop across resistor 1, VR1, is equivalent to 6 volts. So 6 volts. So this is equivalent to 6 times 6, that is 36 milliwatts. So 36 milliwatts. For PR2, we have 6 milliampere multiplied by, okay, let's say we will use the other formula. P is equal to I squared R. So power is equal to the total current, 6 milliampere, multiplied by the resistance across R1s. And we already know that is equivalent to 1 k ohms. So that is equivalent to 43.2 milliwatts. Okay. And for power across resistor 3, so let's say we will use the other formula, V squared over R. So the voltage across resistor 3 is equivalent to 10.8. So we have 10.8 squared over the resistance, which is equivalent to 1.8 k ohms. So just check in the circuit. So we can have power across our resistor 3 is equivalent to 64.8 milliwatts. So we have now, here we have, so we have 36 milliwatts. We have 43.2 milliwatts, and we have 64.8 milliwatts. So notice that if you sum up this power across each resistors, it will add up to 144 watts power delivered from the battery to our circuit. Okay, so this is also another example for series circuits. Okay, so that's all, and thank you.